Hello viewers, today onwards we will start to learn about different components available in SiEPIC Ebeam PDK Process Design Kit. So you can see on my screen this is a document which is available on this GitHub website. Complete link is given here at right hand side. You can see the title of this document is SiEPIC Ebeam. Ebeam is electron beam lithography process and PDK process design kit documentation. So one by one we will take these components, and in a series of this kind of video we will try to complete or we are trying to comprehend the components available. So let us begin. All the components included in this document have compact models, are embedded into the SiEPIC Ebeam PDK in the KLayout under the Ebeam components with models library, and have numerical interconnect compact models for simulation. So in this document, table of content is given like this: description, model, compact model information, parameters, simulation results, experimental results, additional result references. So in this series, first component is adiabatic coupler. I think this is given as per alphabetical order. So first one is this adiabatic coupler. Second one is the brake gratings. Third is broadband directional coupler. Fourth is crossing. Then directional coupler. Sixth is disconnected waveguides. Seventh is fiber grating coupler. Eight ring regulator. Nine taper. 10 terminator. 11 waveguide. 12 wide branch. So approximately there are 12 components, and some of the in appendix this list of components names is given. So let us begin. So first component which is here is called adiabatic coupler. So it was last updated in August 2019. So what is this adiabatic coupler? So adiabatic coupler is nothing but 50-50. This is a say, two input, two outputs are there. So suppose if one input light is there, say 1 milliwatt. So if there is no loss, so 0.5 milliwatt power is available at this port. Say port here 1, 2, 3, 4. So port 3 and 4 is receiving or giving the output as 0.5 milliwatt light output. So this is what is called 50-50. 2 cross 2 broadband adiabatic 3 dB coupler or splitter. So why this 2 cross 2? Because 2 port is here at the input and 2 port at the output. That is why it is called 2 cross 2. Broadband because it supports large range of wavelength, means the splitting and coupling is less wavelength sensitive. So that is why broadband. Adiabatic means again same is this uh, we can change. Let us see how whether we can change or not. This coupling length etc. 3 dB again half power point couplers. So this can be used as a coupler as well as splitter device. So two 3 dB couplers. These two devices. Suppose this is one, and another we can take like this. Then two 3 dB couplers can be used to make an unbalanced MZI interferometers. Means if we suppose we connect here and another one is connected like this, so this will be unbalanced MZI. Here we are using one adiabatic coupler here, another adiabatic coupler here, showing a large extension ratio. So this entire this structure gives large extension ratio. Means the difference between constructive interference and destructive interference is very large. So this is very large, very clear cut splitting ratio is there, so that is why large extension ratio. The advantage of this device compared to Y branch is that it has two cross two ports. So what is this Y branch? Y branch also does the same job of coupling and splitting. Its structure is like this. So here it is working as a splitter. But the same if you flip it, you can see like this. So this will work as a combiner or coupler. So splitter and coupler. So this is a Y branch. Y branch also doing the same job what a Adiabatic coupler is doing, but it's 3 port. However, this is a 4 port, and it has two outputs. This Adiabatic coupler has two outputs. Suppose you can see here, this is output 1, this is output 2. Two outputs are there, and these two outputs are 180-degree out of phase. So sometimes which is very necessary to compare the results. Compared to directional coupler, it is less wavelength sensitive. So broadband directional coupler, as I structure is saying, but this is a adiabatic, so it has been deliberately made to be less wavelength sensitive. Now, so far as structure is concerned, in KLayout, the model name is given eBeam Adiabatic TE mode. So, first one above one is optimize or TE light mode operation at 1550 nanometer central wavelength, and below one is optimized for TM mode, transverse magnetic mode at 1550. So we try to see the results. So here how we will identify these two devices by their name, model name. Now coming to this complex model information, support for TE and TM mode polarization using their respective models, operating at 1550 nanometer, performance TE and TM mode, for use with strict waveguides only, splitting ratio was extracted from unbalanced MZ spectra and excess loss is negligible. So here some result is given, but since they are using MZ, so we have to also design MZ, which will not we will cover in this video sometimes else when we will come with the MZ parameter. So this is the an additional designer tool methodology. So 3D FDTT methods, numerical FDTT solutions were used for modeling this as well as eigenmode expansion solution. And this the parameter which is used to design this adiabatic coupler is given in this paper. 2 cross 2 adiabatic 3dB coupler on silicon or insulator RIP waveguide proceeding this. However, here only strip waveguide has been used, but in this paper RIP waveguide is used. So what is strip waveguide? Strip waveguide is like this, and RIP waveguide has structure like this. So this is the difference between. So strip waveguide is simply like this. However, RIP waveguide has structure like this. So this is strip. This is RIP. It has more concentration of light. However, it needs little complex fabrication step. So let us move to KLayout, how to model, how to characterize it. So we will open our KLayout and switch the screen, top sharing, window, KLayout. Here you are. So you can see KLayout. Let me check. Yeah, I hope it is visible. So start from the floor plan, left right hand side, this floor, go to box, select this box, draw a box arbitrary size, click outside, skip, click here, press Q to select or to edit the box properties. So left corner, x is equal to 0, y is equal to 0, and 605 micrometer we are taking standard value, and here 410 y. So x is 605 and y is 410. So press F, so it is in the center. Now, as usual, we have to select this library Ebeam V0.3.39, and after that registers. From here we are going to select this grating coupler to couple the line because it is essential. So this is a grating coupler. I will select three arrays here and go to this side. Press escape. Since it is not visible, go to full hierarchy. Now simultaneously I will take another grating coupler for TM mode. So it is selected grating coupler for TM mode, and this one I'm doing first time for TM mode. This is here, but I think you need to reverse the direction to consider as a TM mode. Press escape, select again Q. So here rotation angle, let it be 180 degree, so that, yeah, now we can receive 40 mode. So left hand side, so we have to consider this EV adiabatic TE mode here. This is coupler, adiabatic coupler. Okay, instead of doing this, let me select from here. If it is coming like this array, I have to skip, go to registers. Instead of array, I will take only one. So this is TE mode adiabatic coupler. So we'll put here, press escape. I will take this TM mode one also. And now selected, and I will put here. So right hand side TM mode, left hand side TE mode. So now we have considered the components. Now we are going to make the connections, that is waveguide. So material should be silicon. Go to path 0.5 micrometer. That is okay. Now first of all, I will connect the input light here. This let us see whether we shall able to keep this 5 micrometer bed radius perfectly or not. This is, let me check, waveguide, path to waveguide at 5 micrometer. So perfectly right. So this connection is made. So from here I will give input light, and now further output I will connect from here, go to up to here, this side. I will connect to this grating coupler. Here I will put photo detector number 1. This is, go to this waveguide, path to waveguide. This W is the command which we can use also, W to connect. And now the third output, which is here, fourth port basically. And now I'm taking from here, move out, here put and double click, press W, so connection is made. Now this is done here. Now I will make the connection for this. So for TM mode, this is here. I think it require uh, 10 micrometer bending radius, so it has to be larger size. Let me put this uh, getting coupler little bit away so that we can keep bending radius sufficiently large. Okay, so this is silicone material. Now path 0.5 micrometer, and here I will give connection for input light. I do not know whether more this symmetric, since it is a passive, so symmetricity should be there. Control F. Let me connect this and here and here. So this path to be right, but I think it has taken same radius. It should not take. I think I have to change it, delete it, because bending radius I have to consider 10 micrometer. Did not be selected. Yeah, selected now. Go to this somewhere else. Take some other selection. How much it is there? Okay. Click path 0.5. Let us connection. So go back to this. Now actually it should give some radius. I do not know how much this is. Bending radius. Press Q if it is given. Give a guide. Can I change here? Yeah, I can change it. The radius. So yeah, and okay. Now again, so this is the input. Now another port, that is the output. So I will connect from this output port to this side. To here, and this path to waveguide has taken. I have to see whether it is coming. Then property radius. Radius should be 10. If it is okay, it will not give warning, otherwise it should give warning. So now another output which I will consider here. We can skip here. I should double click the blue connection is made. Only issue that I will ensure should be 10 micrometer radius. So I hope I have made the connections. Now go for the text. You see the text. Here text. So I will label it. So this will be broadband adiabatic coupler adiabatic coupler AC. Today is 22. So 22 Jan. So I will put this here at this input. Uh, and again now for second one this will be here. So text this one, but now this will be the M mode, negative coupler, and it should be connected here. Let's escape. And after that, I have to put lasers and photodetectors. So this is the library, and here this is laser. I will put laser here. So for laser, uh, this will be here. What I said mode, not A, to this is box. Let me select this laser, rescue, corner, box property. This is coming. Now I want laser, this laser. So control change, control apply changes. Yeah, Q. Yeah, cell property. 40E mode 1 or 40E mode 2. So whenever I am going to select another laser code, I have to put this as a 2. Okay. So this is laser. I will take laser, one more laser here, and cell property is coming. Yeah, and I will consider here 2, and we'll put now this is. This is laser 2, and now photodetectors. So this is photodetector 1 and 1. Okay, this will be 1, this will be 2, this will be 3, this will be 4. So let us change the word and here 2. Let me change the name 2, photodetector 2. Okay, and this will be 3, photodetector 2, and photodetector number 3, and here photodetector number 4. I think this is not selected. Here photodetector number 4. Okay. I hope everything fine. Let us go for functional verification. So core layout error, what are those? Let us see. I think this is related with disconnected pin. Yeah, it is disconnected pin. Okay, one pin is not connected. Yeah, here that is and here. So we can put here terminator these two and these two pins, and others are this. Automatic pin labeling is already done. I do not know what is this error, but yes, you can still improve by going this ebeam library ebeam component, and there is a terminator for TE mode and for as well as for TM mode. So left hand side is TE, so I will select here and terminator and put here. Press escape, select over it, shift O, so connected. And now with this, so TM mode, this will be 180 degree because we have to move, and let us try to put here this connected pin. So just create it. So skip, select over it, hit shift O, so connection is made. Now go for a get function, so you can find only related with labeling, although we have done the labeling, so it should not be an issue. So we have done our part here. Now we go for the simulation. So circuit simulation. Okay, before that we have to save it. Simulation. Save as this file. I'm saving in this KLayout designs. This will be your adiabatic pretty coupler. So in the folder I will put here adiabatic coupler 42 Jan 2022. Opening it here, adiabatic coupler EE and TM, so 22 Jan 2022. So this is the file name. Okay, so GDS layout has been saved like this. Now after that we can go for simulation, circuit simulation. Okay, cancel. Just here to wait till it open. I will come back again. So before proceeding, let us see again. So what we are trying to do here, we have considered both TE mode and TM mode, adiabatic national coupler. So it support for TE mode, TM modes. These components we have considered. This is the input and these two are the output. So we shall try to see whether it is able to split the light into 50-50 and what are the approximate range of that splitting. So this is the thing. And later on we can make also MZI, but not now. In this, not in this video. Next video we shall try to make. So let me see it's opening or not. Yeah. So I will see another screen in a few seconds. So till this is opening, I will just try to get another one, that is the brake grating, and one more component. Grating coupler we have used. Let us see if it is there. Grating coupler. This is brought by National Coupler. Many times we have read about it. Now this is crossing. In some another video I shall cover it about this crossing. This is directional coupler, and yeah, this is the grating coupler. Let me read because we have used this. we invariably use this fiber grating coupler. So what it is? It is fully etched fiber waveguide grating coupler with sub-wavelength grating showing high coupling efficiency as well as low back reflection for both transverse electric and transverse magnetic modes. That is why you have seen I have used both. This one only just orientation I have changed as per the convention. E-beam fabrication cost is reduced by 2 to 3 times when eliminating the shallow edge. Okay, so model name is this one, E-beam grating coupler for TE mode, E-beam grating coupler for TM. So this TE and another one was for TM. So you have seen I have used T for TE as well as for TM mode. And you can see here operating wavelength 5050 supporting 40 TM mode. 40E mode, the 4.1 dB loss and bandwidth is 30.6 nanometer, 1 dB bandwidth. And for TM mode, 3.7 dB loss and 47.5 nanometer, 1 dB bandwidth. So this is the SEM image. Top view is a figure 2. SEM, scanning electron microscope image of the focusing sub-wavelength grating coupler, top view. This one. And this is the side wall view. So you can see this is the larger, this is the smaller grating, larger, smaller, and this is here. You can see. So now I think uh, extension ratio here for TE mode 0.3 dB, for TM mode 0.15 dB. This is insertion loss versus wavelength. The transmission line, transmission for TE mode it is blue color one, and red one is the TM mode. Okay, this is the 1 dB bandwidth. So from 5040 to 1560 nanometer. And okay, so before going further, let me share my screen. So go for window in here. I hope my screen is visible. So this is Adiabatic TETM board I think is giving the output here. I will just simulate and so found empty result. I think is yeah. So let me actually remove one of the laser so that it should be functional. Otherwise, uh, this I will remove this. Okay, so later we can put detectors. Let us do first for the E mode. So simulation circuit. So what I have done here right now, I'm just at a time I'm simulating only TE mode, not TM. Yeah. So TM one I'm just closing it. Let's say TE mode. Let me share the screen now with this one. So you can see it is grating coupler TE mode. This is the ONA optical network analyzer. So gain curve is here, gain curve for both ports. So let us see. It's simulated. So successful. Go for display. So yeah, you can see. Yeah, there is a power difference. It is not exactly 50-50 because if it is 50-50, both should be coincide. So in the mode 1 is port 3, the light with blue color, port 3 the blue. Let it be light with mm, light with 5. So this is the port 3 above one, and below one we see the green one. So we can make this. Yeah, this is the port 4. So in port 4 more light is there compared to port 3. So this is what is the gate, and of course minus value. So basically these are the losses, not as gain. I will put further loss. So just it will follow above one. Yeah. So you can see here. Now this is the loss one. So loss is visible at 50-50, but power splitting is not exactly 50-50. That I want to say, because if it is 50-50, some gap is there, okay, but more or less following the same path, okay. So this is the adiabatic grating coupler. Now let me check anything more is there. What we can do, go to window, and here is, so this is TE mode. Select rescue cell parameter. So it is the waveguide notes. You have to select view. This waveguide is being selected. I want to select this adiabatic coupler. Rescue. Again it is a waveguide. Okay. Rescue. Uh, Okay, if it is not that, I will take from here adiabatic coupler is and put somewhere here. TE road. It is 0 degree. And here just click and select it now easily. Keyboard. This is not a cell. So we cannot change it the properties. Only whatever it is there, we can use that much only. You not a cell as such. Okay. Now, now this is for TE mode. Let us do the simulation for TM mode. So for that, I have to remove this laser for TE. Okay, laser removed, as well as photo detectors. This and this. So now go for here. So user and user I will put here. This is user, and go for PC cell, TM mode, and here TM mode light, and go for detector. PC cell, okay, detector 1, detector 2, and this. So this Q, I have to give it a 2. So with this now I am going to simulate TM mode light. Simulate, okay, so this was 40E, let me see where's 40E, design, Adiabatic, decoupler, EP, simulation, TM, it has come here, and top, go to window, let me see, it is TM, so the dot TM, I have to close this so that no confusion, window is, yeah, this is TM, so let me save it, save as first, so go to design, Adiabatic, save, but only have to read it as TM. So let us simulate it. I hope it is visible. That is visible. Simulate it. Simulation complete. So save display. This will be. So here for longer wavelength you can see the port 3 is giving more output line than this. And for longer uh, shorter wavelength, this is reverse. So this is difference between T and TM mode, and I can show you the way earlier I showed you for gain loss also, loss curve which will be just reverse of that. So you can see here, so T mode, TM mode. So that is I will save it. So thank you so much. With this you could understand it. You can later on come again to further explore other things inside this circuit. If representing to tab here. So here this is a gating coupler which we have used here. Three gating is total 6 gating coupler, but 3 gating couplers are used for taking the input and output. As an IO device, we use this gating coupler, fiber gating coupler. So this is this device, first one, adiabatic TE and TA both national coupler or 50/50. Thank you so much.